So let's continue with the example that we left off with in the previous lesson. So we had calculated the expected values for this contingency table, and we started to investigate if there's a relationship between adults over 50 who exercise regularly and low, moderate, and high blood pressure. So we're looking to see if there's some sort of relationship between how much they exercise and their blood pressure. So we have all the observed values, and what we calculated was assuming that these classifications are independent, what we would expect, how many people we would expect to fall into each category. So that this is where we left off with the expected values. So what I was saying at the end of the last lecture is that now we want to calculate a statistic to determine whether the differences between the observed and the expected frequencies for all the cells in the tables are large or small. This calculation that we're going to make is called Pearson's chi-square test statistic. And this here is chi-square. That's what we call that notation. So chi-square. And the way we get this calculation is we sum up the difference between each observed and expected value squared. So all those, for each cell, we're going to take the observed value and the expected value, square it, and divide it by the expected value. So remember, O is the observed cell frequency, E is the expected cell frequency. So if we look at all these squared differences and divide by the expected value and sum, all these up, we're going to get this chi-square test statistic. A large value, so this is important. So this is how we interpret this chi-square test statistic. A large value of chi-square indicates a significant relationship exists between the two classifications. So that indicates that they're not independent, that they are in fact dependent, and there's some relationship. So we need to determine how large a value of chi-square would indicate that the two classifications are dependent. So in order to determine when a value of Pearson's chi-square statistic is considered to be large, we need to examine a distribution that consists of all the possible values of the chi-square statistic. And this distribution is called the sampling distribution of Pearson's chi-square statistic. And the sampling distribution of Pearson's chi-square statistic is approximated by a chi-square distribution. And it's denoted as the chi-square distribution if we want to use symbols. So far, we've worked with the normal distribution and the t-distribution when conducting a hypothesis test. Now we have this new chi-square distribution. So let's just talk about some properties of this chi-square distribution. So since we're summing up all these square differences, the value of chi-square is always positive or non-negative. The graph of a chi-square distribution is not symmetric, it's skewed to the right and extends infinitely to the right of 0. So when we look at our picture for a chi-square distribution, it's always going to be skewed to the right. Similar to the t-distribution, it has its own degrees of freedom, or df. And those degrees of freedom are calculated by taking the number of rows minus 1 times the number of columns minus 1. So when we make that multiplication calculation, that's going to give us our degrees of freedom. So whenever we're going to test independence, we're going to use a right-tailed test on the chi-square distribution. And this is because we're testing to see if the chi-square measure of the difference between the observed and the expected frequencies is too large to be due just to chance alone. So let's go through the steps for constructing a chi-square hypothesis test for independence. It's really the same 5 steps that we used when we were conducting a hypothesis test on means and proportions. It's just now we're using a different distribution. So in this case, we're using a chi-square distribution. When we were testing proportions, we were using a normal distribution. And when we were testing means, we were using a t-distribution. The first step is still to formulate your hypotheses. That's not going to change. The null and the alternative have to be stated first. And alpha also, I should have added that here. So, and also we state our level of significance alpha. So when, like I mentioned earlier in this lesson and the previous lesson, we're always under the assumption that the two variables are independent. So my null hypothesis is always going to be independence. Now we're challenging that, right? Because we're assuming that to be true. We're always assuming the null is true, remember? So the alternative is what's suspected to be true. So it's going to be the opposite. So the alternative in a chi-square test is going to be that the two variables are dependent. And that's what we're trying to prove. We're trying to see if our chi-square test statistic is large enough that we can reject the null hypothesis of independence and conclude that the variables are dependent. So how do we do that? Well, the first step is what we did in the previous lecture. For each cell, we want to compute the expected frequency E. So I rounded above just to make it easier on us. The reason here it says do not round, but give as a decimal number is because the more precise we are, the more precise our chi-square statistic is going to be once we calculate it. I'm going to be doing this in the calculator using a chi-square test for independence, so we're not going to have to worry about it. This would be if we're doing it by hand every single time. So let's continue, and we'll use the values that I calculated above here, even though I rounded them. But going forward, you know, normally we wouldn't round like that. I'm just trying to make our life a little bit easier. So we said this is how we get the expected values, right? We take the row total times the column total, divide by the sample size. So next, what we have to do is we have to compute the sample chi-square test statistic. And the way we get that is we sum up all of the differences between our observed and our expected value squared divided by the expected value. And then once we get that chi-square statistic, we're going to be able, I'll show you how to find the p-value of the test. And remember, we were finding the p-value when we were testing means and proportions. The same decision rule is going to apply. Remember, in order to conclude our test, so step 3 to be to get the p-value, step 4 is our decision rule, right? Remember, if the p-value is less than alpha, then we reject the null hypothesis. It's going to be the same decision rule for chi-square test as well. And then step 5, I'm always going to have you state your conclusion in the context of the application. So that's how we're going to conduct a chi-square test for independence. So what I want to do is let's calculate by hand, and this is the only time we're going to do this. And then going forward in the next lecture, I'm going to show you how to use the calculator to get your chi-square test statistic and your p-value. But I like to do it once just to show you how to get this statistic by hand, because I think it's important. So let's get the chi-square statistic for the previous example that we did up here. So the example with exercise and blood pressure. So now what I want to do is let's calculate the chi-square test statistic. So we're going to sum up each observed minus the expected value squared over the expected value. So what we're going to do is for each cell, we're going to take the observed value. So look, for cell 1 up here for a low and regular exercise, we're going to take the observed, which is 35. And we're going to minus the expected, which is 29. We're going to square it, and then we're going to divide by the expected value of 29. We're going to do that for all the cells, and we're going to sum up all those calculations. So for the cell underneath it, for low and no regular exercise, we're going to take the observed, which is 21, minus the expected, which is 27. We're going to square it and divide by the expected, which is 27. So let's keep going. So then we're going to take 62 minus 66 squared divided by 66. Then we're going to take 65 minus 61 squared divided by 61, plus, now we have to do the last two cells in that last column. So we'll do plus 25 minus 27 squared divided by 27. And then plus 28 minus 26 squared divided by 26. And if we were to plug this into the calculator, we get about 3.38 for our chi-square test statistic. And this is going to have a little bit of rounding error. And you could pause here if you'd like and plug that sum into your calculator exactly as you see it and make sure you're getting 3.38. But like I said earlier, we're never going to have to get this by hand again. There's a function in the calculator that'll calculate chi-square for us. We're not going to have to do this again. But I like to do it at least once with you so you could see where this value comes from in the calculator. So now what we do is we have to see, is this chi-square large enough that we're going to consider these two classifications to be dependent? So we'll talk about, in the next lecture, first of all, how we can get this calculation using the calculator. Okay, I'm going to show you a function in the calculator to do this. And then I'm going to show you how to determine the p-value and then how we can make our decision.